to this. Thank you. So my name is Filipe, and I'll show you a bit of my research at Aston University in the UK. I'll give a very brief introduction to the work, show you some methods I used, results from dye adsorption with char, how they correlate with char quality and slope pyrolysis conditions, and then some conclusions. So my work is with the GreenCarbon project within Work Package 4, thermochemical processes for mainly lignocellulosic feedstocks. The project allowed to do some interesting interactions with other students, so providing data for the other researcher at Aston and also the researchers at Zaragoza University and Ghent and Edinburgh University. That's really interesting and good due to the GreenCarbon projects. So in terms of my work, the main thing is doing slope pyrolysis of wheat straw in a continuous screw reactor, lab scale, studying how the temperature, the residence time of the solids, and the use of carrier gas affects the product yields and the properties, and focusing on the char products. And then applying the chars to remove contaminants from water, organic contaminants, and I chose a dye as a model compound, which is usually used in research. And then trying to optimize the process for this decontamination, including modifying the process to incorporate activation strategies in one step. So then trying to get a more sustainable replacement for activated carbon, which is usually used for adsorption of contaminants from water, because traditionally activated carbon is made through time and resource consuming processes and also unsustainable feedstocks like coal and coconut shells. So there's plenty of research now on trying to develop replacements, and that's what I work on. So you can see a picture of the feedstock as received in broken pellet form, the wheat straw. I studied 3 different temperatures and 3 different solid residence times, which was limited by the screw speed. Then I tried to implement modifications similar to activation in one step, but more mild, let's say, to make it more sustainable, the process, and more cost-effective, probably. So instead of injecting steam in physical activation, I artificially raised the feedstock moisture content to 50 and 75% using different ratios between water and the feedstock. This is what the feedstock looks like after the soaking. So the particles crumble up, they disintegrate. I also tried using CO2 as carrier gas, compared with using nitrogen or not using carrier gas at all, which is possible with the screw reactor. And I also tried merging the slope pyrolysis with chemical activation with KOH by wet impregnation of the feedstock with different KOH concentration solutions. And for these modifications, I chose the lowest and highest temperatures I used before to compare the effects and see the differences. And I chose the highest residence time because I wanted the highest time of exposure between the CO2 or the steam with the solids, because activation is usually done at least 1 hour activation, or can be less, but traditionally at least 1 hour. So this was the maximum possible. And then the adsorption, I chose methylene blue, which is the most popular dye used in adsorption to test the capacity of adsorbents. It has alkaline character. It looks like a very dark blue in the color in water, and it gets decontaminated and decolored. I did batch tests. I mixed a certain amount of ground and seed char with the stock solution for 3 hours at 50 Celsius. Then I separated them and measured the final concentration with UV visible spectroscopy. So in terms of, I will show the maximum removal of the dye at equilibrium, just to simplify. And these are also preliminary, not very in-depth tests. So I'm going to show mainly the maximum dye removal. So I compared the chars with also a commercial activated carbon, which was like the control experiment. So it removed 99% of the dye, as expected. And then what I found with the increasing pyrolysis temperature was that the adsorption capacity decreased. So the highest was with the 400-degree chars. And there were some contrasting trends with the solid residence times tested. So with the different modifications I did, starting with the experiments with the feedstock with elevated moisture content, I found the same thing. So the lowest temperature obtained the highest adsorption capacity, slightly higher, or let's say it didn't decrease it at least, which is good. And at the highest temperature, no significant change occurred. The CO2 as carrier gas, I saw that the CO2 experiments gave higher capacity than using nitrogen or no carrier gas, which is interesting. And this again occurred at the lowest temperature tested. At the highest temperature, there was no significant difference between the carrier gases. For the charts from experiments with KOH, I found again the same thing. The highest adsorption capacity was with the lowest temperature tested, and I found the highest removal of dye at the 400-degree char with the lowest concentration of KOH, which was again an interesting finding. And the highest concentration actually decreased the capacity. And again, at highest temperature, it was not possible to achieve these values, but there was an interesting increase for the highest concentration of KOH. So then, trying to explain what's happening, what's the mechanisms, I tried a different dye. So now an acidic dye, methyl orange. Again, the activated carbon removed pretty much all of the dye. And what I found now was that the removal value could not be achieved as high as methylene blue. So only 23% maximum removal with 400-degree char and 4% with 600-degree. And then when I tested different chars from the modifications, I found that the maximum removal of all was 38%, and this one was achieved with a 600-degree char at one of the elevated moisture contents chars. So this was the maximum removal of all the chars I produced. In terms of the other modifications, at 400 degrees, there was a decrease in the adsorption capacity with the modifications, and even one of the chars did not remove this dye at all. And at 600, there was no increase besides the 38%, which was the maximum. So this is suggesting me that it's the chemical functionalities in the chars causing the high adsorption of methylene blue for the lowest temperature chars. So oxygen functionalities and pH contributing to this, and not porosity as could be expected. I'll show first the porosimetry results with nitrogen. This is the typical isotherm, what it looks like for all the chars, very similar to this one. It's just an example. So the maximum surface area with BET was around 8 square meter per gram, which is very low, and this was obtained with the lowest temperature char, one of the elevated feedstock moisture content experiments. And again, the commercial activated carbon obtained over 600 square meter per gram surface area, which was expected. And for the chars, this value was not achieved for any of the modifications I did. So this is suggesting the chars are non-porous or have narrow micropores, which is usually assessed with the CO2 porosimetry, which is recommended. From the tests I was able to do, it's indeed suggesting that there is narrow microporosity. So I saw that the surface area with CO2 would increase with pyrolysis temperature up to 100 square meter per gram. And indeed, there can be some narrow micropores there. In terms of other properties, I studied the proximate analysis of the chars. So from the elevated feedstock moisture contents, I saw a slight increase in volatile matter compared to the normal slow pyrolysis chars. And this was due to a reduction in the time available to carbonize the material. So there's more moisture, there's more energy expense and time to remove the moisture first. I also saw an increase in oxygen and decrease in carbon, however, only for the lowest temperature chars, which was interesting. I also did the infrared test, and the top three lines are for the 600-degree chars and the bottom three for the 400. So the 600-degree chars, there are no significant differences between the spectra, but for the 400-degree ones, there are some increases in some of the functionalities, including the carbon-oxygen functionalities, which is really interesting, and I related this with the improved adsorption for the elevated moisture content chars at 400 degrees.
You have 2 minutes left, Filipe.
Thank you. So for the chars from using CO2, overall, I found lower volatile matter content, and that the CO2 had stronger effect than the other options. This was again connected to that improved adsorption I found before. As for the ultimate analysis, at the lowest temperature, CO2 had an effect and nitrogen did not. And there was an increase in oxygen content, which again was related to this adsorption and more chemical functionalities to remove the methylene blue. In terms of pH, the CO2 chars were slightly more acidic, which was also connected to this oxygen functionalities. And there were other surface chemistry changes for 600 degrees. As for the KOH chars, I saw an increase in volatile matter with the KOH ones and increasing with KOH concentration. The ash content increased significantly, especially for the 1 molar KOH. And this, I assume, is covering the surface and the pores. So I related this to the decrease in adsorption I found for the 400-degree char with 1 molar KOH. As for the ultimate analysis, I saw an increase in oxygen content for the lowest temperature and lowest concentration, which are related to the improved adsorption, the 99% removal I found for this char. As for the pH, I found the chars to be more alkaline, and overall, the KOH included some functionalities, including oxygen, and at the lowest temperature and KOH concentration, more CO groups were found compared to the 1 molar. And this was again related to the best adsorption found. To conclude, to summarize the findings, char from the unmodified slow pyrolysis at the lowest temperature was able to remove the dye from solution, the methylene blue, at comparable efficiencies comparable to activated carbon. The surface chemistry is playing a more important role than porosity for the chars, which is interesting. And the modifications do not promote porosity increase or activation itself due to the reactor configuration. So there's a high contact time between vapors and the solids, which maybe is incorporating tars or other compounds in the char, blocking the sites, and also the mild conditions that were applied. Specifically, there was a slight improvement for the elevated feedstock moisture content for lower temperature due to functional groups. The same thing occurred for the CO2 experiments. As for the KOH, also a slight improvement for the lowest concentration at lowest temperature due to, again, to the oxygen groups, but an opposite effect with the highest concentration, likely due to inorganics covering the surface and the pores. So that's my presentation. Thank you. If you have any questions, email me or ask now.
Thank you very much, Filipe. We're really late in time, so you got some questions, but please answer them in the chat directly.